Welcome to NKT Photonics. My name is Thomas Olsen. I'm Director of R&D for the Koheras product line. We're here to look at how we develop the world's most silent lasers for quantum applications, how we develop fiber lasers, amplifiers, frequency conversion, fiber deliveries, and complete solutions for quantum and beyond.
My name is Asger Jensen. I'm Head of Quantum here at NKT Photonics, and I'm standing in one of our many research labs. And in these labs, we developed the next generation of fiber amplifiers and fiber lasers. Fiber lasers and amplifiers is a unique platform based on our photonic crystal fibers that allows you not only to scale power to incredible high powers compared to most other laser systems, but the fiber laser platform that seats this whole thing also has its own unique properties that lends itself very nicely to some of the cutting edge technologies that you'll find fiber lasers in. That could, for instance, be quantum optics, where the extremely narrow line width and low noise properties and mode hop free tunability lends itself very nicely to where quantum computers, quantum sensors and quantum metrology systems needs to be over the next few years.
Now we are going to what we call the UV room at NKT Photonics, and it's where we make the core component of our product on the Koheras line, and this component is a raw fiber laser. So please follow me into the UV room, and safety first, so we use protection goggles because we have a high energy UV laser in there. So here we stand in the UV room, and as I mentioned, we make the core component of the Koheras products, which is a raw fiber laser. And this is also the first product that Koheras sold back in the days. And the raw fiber laser consists of a laser cavity inscribed into a glass fiber. And this glass fiber is active, so it has been doped with atoms like erbium, ytterbium, or thulium in order to provide gain energy for the laser. So to make this laser cavity, we write Bragg ratings with high energy UV lasers. And as you can see here, it's our setup for UV writing, where the UV laser stands behind the writing station. And we have some optics to shape the beam and direct the beam onto the glass fiber. So once the UV beam reaches the station where the fiber is placed, on top of the fiber we have a phase mask. So the phase mask that we come and place on top of the fiber, so that it creates interference pattern that would be inscribed into the glass. For making this laser cavity, we need a high reflector and an output coupler with a lower reflectivity, so that we can direct the light out of the fiber cavity. And since we are always at the forefront of fiber laser technology, we often have the need for specific equipment in our production and here in this UV room, so that we can make new products and in a more efficient way and in a more reliable and sturdy way. So here is a production area, so there is a lot going on every day, and all what we make in this room needs to be sturdy and easy to use for the production technicians. And we have a lot of work to do to get equipment that is right for the job. And for that we have very nice collaboration with our supplier of equipment, with who we often cooperate to develop the best piece of equipment for our facilities. So a very important piece of equipment that we have here, beside the UV laser, are spectrum scanners to check the quality of the process and of the product that we made here, which is a raw fiber laser. So on the screen here you can see a real-time scan of the transmission through our raw fiber laser. And we can clearly see a dip in transmission that indicates the position of our grating. And this is a very important information for us in our production because we need to hit the right wavelengths for the laser we produce. And we have a bunch of parameters that needs to be fulfilled when we are making our raw fiber laser. And with this equipment, we can test for that.
After we've made the core of our product, being the raw fiber laser, we will bring it out here, which is the main production line of the Koheras fiber lasers. And now we need to build all of the supporting optics and electronics around the raw fiber laser. And the first thing we want to do is we want to fixate the raw fiber laser into what we call a substrate, which in this case is aluminum. Fixating the fiber laser will enable us to thermally control the temperature of the fiber laser, and since aluminum has a higher thermal expansion coefficient than glass, we can also make a coarse tuning of the wavelength of the fiber laser. A lot of customers also want to be able to have a much faster wavelength tuning to, for example, lock to an atom or whatever. And then we also supply a piezo on this substrate. And so you could say you have the slow thermal tuning to do a coarse tuning of the wavelength. And then you'll have a faster but smaller tuning using the piezos to do the fine tuning and locking to, for example, an atomic transition. We still need to do a lot of other supporting optics and electronics before it's a module. And I have an example of this here. So the fiber laser is going to be spliced into what we call a module. This is our smallest module called a basic micro, where you have the fiber laser now inside a thermal shield. You have some pump diodes and you have some supporting optics. And you have a photodiode that will allow you to make an electronic feedback loop to stabilize the power. And the electronics also support stabilizing the temperature of the module. The smallest basic micro module is preferred by OEM customers who want to integrate the fiber laser into their own products. After a module has been spliced, it needs to be tested. First of all, to be calibrated. Power-wise and wavelength-wise, but we also need to verify all of its performance parameters. And the calibration and verification of performance parameters is done automatically. So we have built automatic test setups that will enable us to calibrate and verify the performance of all of the modules.